Let's talk a little bit more about resistance. Now, manufacturers produce resistors that you can use in a lab, but also that you can use in actual electrical engineering setups. For example, your cell phones are full of resistors, little devices, little tiny pieces of metal or some material that adds resistance to a circuit. Why would you want to do that? So that you can get the right amount of current flowing through your phone. So this figure on the left is an image of a very typical standard resistor. They usually have multiple colored bands, and the colored bands help us to know what the resistance is. The way that this works is you have 4 bands, so we're going to have 4 spaces. 1, 2, times 10 to the power of 3 plus or minus 4% error. So it gives you a number. Oh, and this should be in ohms. It gives you a number. The first 3 bands help to indicate the actual resistance, but then you have a tolerance, in other words, a range of error that your resistor can be in. The first band, the number goes right there, whatever that number is. The second band in color indicates a number, which you put there. And the third band gives you another number that you put in the exponent times 10 to the power of whatever that number is. And the fourth band you put in your error. Now the numbers that you put in these 1, 2, 3, 4 spaces depend on the color, and you have this table in your book, but the color will denote the number. So for example, here in this figure, you have red, green, yellow, silver. So red means 2. Green, so here's red. Green means 5 times 10 to the power of yellow. That's a 4, so 10 times 10 to the power of 4 ohms. So that's 25 times 10 to the 4th ohms. That would be 250,000 ohms. And the tolerance is silver. So the tolerance is over here, 10%. So this is plus or minus 10%. And that is how you determine the resistor that you're looking at based on the color codes. Now, what determines the resistance of a wire? Well, there are 3 things. The first 2 things are the length. The first thing is the length. The longer the wire is, the more material you have to pass through. So if you increase the length, then you increase the resistance. Therefore, length and resistance are directly proportional. However, the resistance is inversely proportional to the cross-sectional area. Think of it this way. If you have a small wire versus a very thick wire, there's more room for charges to flow in the thicker wire, whereas there isn't as much room in the narrower wire. So since you can have more charges flowing through a thicker wire, it doesn't impede the current as much. So the resistance is inversely proportional to the area. The third thing that the resistance depends on is the material itself. Is it going to be a good conductor like copper? Is it going to be a semiconductor like silicone? Or is it going to be a non-conductor or an insulator like wood? Those are extreme examples, but every material conducts electricity a little differently. And so we indicate that characteristic here using the Greek letter rho, and this is called the resistivity. Resistivity is simply a characteristic of the material. We don't care how big it is, how long it is, how wide it is. All that we care about is what it's made of, and one other thing which I'll explain here in just a second. Here, this is a table in your book, table 18-1. You'll want to note this because you will have homework questions where you need to find the resistivity of certain objects. And that resistivity you can find in this table in your textbook. And so you have all of these coefficients for your, sorry, not coefficients, all these values for your resistivity in this column for all the materials on the left side. Now, a very important thing to note about this table, and that is, can't really see that, but there you go. All of these resistivities are good at a temperature of 20 degrees Celsius. In the last slide, I said that resistivity is a property of the material and one other thing. That other thing is temperature. And in order to account for the temperature, we'll have an equation. I'll show that to you on the next slide. But we account for the temperature using this temperature coefficient here, which is also in this table. And to correct for any changes in temperature, here's the equation we use. The resistivity at some temperature T is going to be the resistivity at a known temperature. For us, that would be from this table, 20 degrees. So we're going to say that R0 is equal to the rho 0 is equal to the resistivity at 20 degrees Celsius. And that's going to be multiplied by this large quantity, 1 plus your temperature coefficient times your change in temperature. This is the temperature at which you're determining the resistance, and T naught would be whatever your reference temperature is. In this table, our reference temperature is 20 degrees Celsius. So if you get the resistivity from that table, T naught is going to be 20 degrees Celsius. Doesn't matter if it's in Celsius or Kelvin. It doesn't, because if you convert it to Kelvin, you're going to have the same change in temperature, because that's really what we're dealing with here, is a change in temperature. Now, this works for conductors. Semiconductors are rather complex materials, and you may have some anomalies that happen. You may increase the temperature and have the resistivity decrease. It could happen. And insulators have very little resistance, and so that's just a completely different ball of wax. No pun intended, since wax is a resistor. Excuse me, wax is an insulator. Anyway, there you go. So semiconductors and insulators are more complex to deal with, so this equation works really well for conductors. Now, since resistance is just equal to the resistivity times the length over the area, that means that not only is the resistivity dependent on temperature, but the resistance is as well. And if we just multiply this equation in the previous slide by length and divide by area, it just converts everything straight to resistance. So it turns out that this equation works well for resistance as well as resistivity. This gives us two really cool things that can happen. The first is the principle of a thermistor. Back in chapter 13, when we were talking about temperature, we talked about two different types of thermometers. One where you have a liquid in a bulb, you heat up the liquid expands. The second one was a bimetallic strip where you have two pieces of metal that expand at different rates. And since they expand at different rates, as they heat up, they'll expand, they'll start to coil. So those were the two types of thermometers we talked about then. Here's a third type of thermometer. A thermistor is a thermometer that uses resistance to determine temperature. When you get in your car and you start it up and it tells you that outside it is 82 degrees Fahrenheit, how does it know that? Well, somewhere there is your car battery, blah, 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 and somewhere along down the line, you're going to have a resistor of some sort. This is the symbol for resistor, by the way. That is a resistance R. So this resistor in your car is exposed to the air around the car. So as you're driving along, it's out there. And then the battery just every once in a while sends a quick circuit current through that resistor. And by measuring the current, it uses Ohm's law, it can measure the resistance. Now, we know what the resistance should be. The resistance should be R naught. But if the temperature changes, then that's going to change the resistance. And so you can find out the new resistance. And by knowing the new resistance, you can find out what that change in temperature is. And thus, the computer just calculates what is the temperature outside. That's how a thermistor works. There's something else that's really cool that happens with resistance. As temperature drops, so you have a dropping temperature, then your change in temperature is going to be negative. And if that's negative, then that means that your resistance is also going to drop. So a dropping temperature means you have a drop in resistance. So if we were to graph that, you would get this line right here. And theoretically, this line should just keep going on and on and on until it drops down to 0. But it doesn't. This is a really weird thing that happens. For every material out there, there is some temperature where when you reach that temperature, suddenly your resistance drops to 0. And any temperature below that critical temperature, you have 0 resistance. This is something we call a superconductor. Why? Because if you look at Ohm's law, your current is going to equal voltage divided by resistance. If your resistance drops to 0, what's going to happen to your current? It's going to shoot through the roof. Your current is going to be very, very large. In fact, as the resistance gets closer and closer to 0, your current would end up getting closer and closer to infinite. Imagine what you can do with an infinite current and 0 resistance. You can do so much. You can transport energy from a power plant to a home with 0 loss of energy. And that would be amazing. And there are lots of research projects going on out there to try and figure out how to create superconductors at normal temperatures. We're not there yet, but it's getting closer, and it's pretty cool to see what they've come up with. So maybe at some point we can actually get to that point where we have 0 resistance and thus current that will not die out.